Okay, we're going to start this polynomial review packet. We're going to take a look at the function f of x equals x to the fourth minus 3x cubed plus 4x. So first we can name and classify f of x based on its degree and number of terms. So we have a degree 4, so we call this a quadratic. And we have 1, 2, 3 terms, so we call this a trinomial. Okay. As we just mentioned, the degree is 4. That is the highest exponent of any of our terms. The leading coefficient of that term x to the fourth is positive 1, is our leading coefficient. And because we have an even degree polynomial function with a positive leading coefficient, our end behavior is going to look something like this, which means that as x goes to negative infinity, f of x is going to go to positive infinity. And as x goes to infinity, f of x also goes to positive infinity. So the idea is as we put in larger and larger or more negative values of x, either way, our outputs are going to get increasingly large. They're going to go up and up and up towards infinity. To determine whether x minus 2 is a factor of f of x, one method that we have for this is to do polynomial long division. So we can set this up. X minus 2 is our divisor. We can use our original polynomial function x to the fourth minus 3x cubed. I'm going to put in a 0x squared as a placeholder and plus 4x. Okay. So we can use our original function f of x as the dividend. And when we're dividing polynomials, we want to focus on the first term. So x goes into x to the fourth, x to the third times. Then we multiply x to the third back by our x minus 2. X to the third times x gives us x to the fourth. X to the third times negative 2 gives us negative 2x cubed. We make sure that we are subtracting each of these terms. X to the fourth minus x to the fourth is 0. Negative x cubed minus negative 2x cubed. Well, that is like plus 2x cubed, so we end up with negative x cubed. We can bring down our remaining parts of our polynomial. So we have 0x squared and 4x. Again, we are just focusing on the leading term. So x goes into negative x cubed, negative x squared times. Okay. Multiply negative x squared back by our divisor, and we are going to say negative x squared times x gives us negative x cubed. Negative x squared times negative 2 gives us 2x squared, and we make sure we subtract. So these cancel, and we end up with negative 2x squared plus 4x. We look at our leading term. X goes into negative 2x squared, negative 2x times, sorry. And then negative 2x times x gives us negative 2x squared. Negative 2x times negative 2 gives us positive 4x. We subtract all of this, and we are left with a remainder of 0. So because we have a remainder of 0, we would say yes, x minus 2 is a factor of f of x. Okay? And the reason is the remainder is 0. Knowing that x minus 2 is a factor, we now can fully factor f of x. So we could write our polynomial f of x in partially factored form using our divisor of x minus 2, which we determined was a factor, and our quotient of x cubed minus x squared minus 2x. Because we know that when multiplied, these are equivalent to x to the fourth minus 3x cubed plus 0x squared plus 4x. So it's equivalent to our original function f of x. Now we can look at x cubed minus x squared minus 2x, and we can say we have a greatest common factor of x that we can pull out. So we could say x minus 2, we pull out x, and we are left with x squared minus x minus 2 when we factor out a GCF of x from each of our terms. Now we have x squared minus x minus 2. This is a quadratic form polynomial, and we have some tools to factor these. So one of our options is we can look if there's anything that multiplies to negative 2 and adds to -1. And in fact, there is. We could do, let's see, -2 and +1. So this can factor into x minus 2, x minus 2, and x plus 1. So this would be a fully factored form of f of x. We may choose to notice that we have a repetition of x minus 2. So we could write this also as f of x equals x plus 1, x minus 2 squared. So both of these are valid ways of writing it in fully factored form. To sketch our graph of f of x, we need a couple of key pieces of data. So one, we want to think back to our degree, which we said was even, of 4, and our leading coefficient, which we said was positive. So we know that our end behavior is going to look something like this. And it may be smooth, we may have some peaks and valleys, but we know that at some point the function is going to end in the positive direction, both on the left and right sides. We also know that we have a y-intercept, okay? And that occurs if we plug in 0 for our function. So if we look back at our original function and we substitute in 0 for our x's, we can see that f of 0 equals 0, which means that the point 0, 0 ends up being our y-intercept. So we have a y-intercept at 0, 0. Our x-intercepts, we can use our factored form in the zero product property. We could say that x equals 0, x plus 1 equals 0, and x minus 2 equals 0. And this means that our x-intercepts will be at 0, 0. We will be at -1, 0, and we will be at +2, 0. And this x-intercept with 2, 0 has a multiplicity of 2, which means that we are bouncing off the graph at this point. Okay, we bounce off the x-axis. The multiplicities of 1 means we cross the x-axis at these points. So let's get those points plotted, and then we'll find a way to connect our graph such that we cross where we need to cross and we bounce where we need to bounce, and our end behavior matches what it should be. So our y-intercept here is at 0, 0. We have an x-intercept at -1, 0. We also have an x-intercept of 2, 0, and we know that we're going to have to bounce off this point. Okay, so I'm going to start on my left, and I know the end behavior is that as x goes to -infinity, f of x goes to +infinity. So I'm going to start my graph something like this, and we're going to come down until we go through our point -1. And we know we cross the graph at this point because it has a multiplicity of 1 for this x-intercept, meaning we cross the graph. To get back through our y-intercept and also our second intercept, x-intercept, we're going to have to turn around and cross back up through our graph. And then to get back down to our x-intercept of 2, we're going to have to turn around again. And then we're going to bounce off this and complete our end behavior. Okay, so this is a rough sketch of something that our graph may look like. Obviously, this is not perfect, but we just want to sketch some of the key details and get a general picture of what our graph might look like. Okay. Final part of this question says state the intervals where f of x is positive and where f of x is negative. So this is saying where are our outputs or our y coordinates positive and negative. So f of x is positive if we are above the x-axis. Okay. If I look, I can see that here my function will be positive, here my function is positive, and here my function is positive. So anytime f of x, or the graph, is above the x-axis, that is when we are positive. So we are positive for inputs of -infinity, I'll fix that, -infinity, all the way up to -1. Okay, and we're not going to include -1 because at -1 the function is 0, and 0 is neither positive nor negative. Then we're negative for a bit, and then we come back and we become positive again at 0, and then we stay positive until we get to 2. Okay. And then we are also positive from 2 to infinity. Okay. So technically we're not positive at that point 2 comma 0 because it is an output of 0. And then the place where we are negative is just when we are below the y-axis. We can highlight that in a different color. So this is the part of our function that dips into the negative area. So our negative interval is from -1 to 0. Okay. And when we state these intervals, we are stating the x values or the inputs for which the function provides positive and negative outputs. So everything that I'm writing here, these are describing x values. And so it's saying when my inputs or my x values go from -infinity to -1, the function's positive. And then when the x inputs are from 0 to 2, function is positive. From 2 to infinity, the function is positive. Okay, so that summarizes our first problem. It gives us practice naming our polynomial, gives us practice talking about end behavior, using notation. We have a sketch of our graph. We can check factors through polynomial long division. We practice factoring. So we have a lot of different things going on here. Our second problem is going to let us test these skills again. So if we go to number 2, we have a new polynomial function f of x equals x cubed minus 3x plus 2. So in this case, our degree is 3. That is our highest degree of any of our terms, or the highest exponent of any of our terms. So we would say this is a cubic. And we have 3 terms, so it is a cubic trinomial. Okay. We just said the degree is 3. Again, our leading coefficient is +1. And our end behavior, well, our cubic function is an odd function. It looks something like this when graphed. So as x goes to -infinity, f of x also is going to -infinity. As x goes to +infinity, f of x also goes to +infinity. Okay, so as we put in bigger and bigger inputs to x, we get larger and larger outputs. As we put in more and more negative inputs, our outputs are increasingly negative. Determine whether x plus 2 is a factor of f of x. So again, one of our methods here, which is good practice, is to take the long division of our polynomial. So we can say x cubed minus 3x plus 2 divided by x plus 2. And we will know it's a factor if we have no remainder. When we do our long division, we're going to look at the leading terms. I'm actually going to add in, again, 0x squared as a placeholder to help keep track as we go through our algorithm for long division. X goes into x cubed, x squared times. Multiplying back, we get x cubed plus 2x squared. And we remember we need to subtract because we want to see the difference between our original polynomial and what we have so far. Cancels. We get -2x squared minus 3x plus 2. We look at the leading terms. X goes into -2x squared, -2x times. We multiply it back. We get -2x squared minus 4x. And we make sure we subtract. We end up with -3x minus -4x. It's equivalent to plus 4x. And we get x plus 2. And then x plus 2, well, x goes into x one time. We multiply it back, we get x plus 2. And we find a remainder of 0. So again, we would say yes, x plus 2 is a factor, okay, of f of x, because we have no remainder, or a remainder of 0. Again, we can fully factor f of x, so it makes sense to use our divisor, x plus 2, multiplied by our quotient, x squared minus 2x plus 1, because these we know when multiplied are equivalent to x cubed minus 3x plus 2. That's our original polynomial f of x. This is just a factored form, so we're closer to being fully factored. Here we can see x plus 2 minus 2x plus 1 is a quadratic, so we can use our methods for factoring quadratics. We can say, does anything multiply to positive 1 and add to negative 2? And the answer would be negative 1 and negative 1. So we can say x plus 2, x minus 1, x minus 1. So that would be an example of a fully factored form of f of x. We may also choose to write this as x plus 2, x minus 1 squared. So either of those are valid fully factored forms of f of x. To sketch our graph of f of x, we think back. We said this was an odd degree. We had a degree of 3, and it is a positive leading coefficient. So our degree was odd. We had a positive leading coefficient. That means our graph's going to look something like this. Okay. And then we're going to use our key coordinates, so a y-intercept. Well, if we put in 0 for our x's, f of 0, we can see all that remains is 2. So our y-intercept is 0, 2. Our x-intercepts we can get from our zero product property. So we would have negative 2, 0, and we would also have 1, 0. And that 1, 0 has a multiplicity of 2, which means we're going to bounce off the graph. Okay. As far as the negative 2, 0, that's a multiplicity of 1, so that means we cross the graph here. So we're going to plot our key points and then try to make our graph match what we know it should look like. So we're going to put a y-intercept at 0, 2. We can put an x-intercept at negative 2, 0. We can put a x-intercept at 1, 0. We know that we begin with negative end behavior on the left. We come up. We have to get through our y-intercept. And then we're going to come back down and bounce off the graph. Let me try a little better there. So we're going to come up, go through our y-intercept, come to the x-intercept, and bounce off the graph because of our multiplicity of 2. So this is a general rough sketch of what our graph might look like. Okay. Now we check the intervals where we're positive and negative. So first we can look at where we're negative. The only part of our graph that's negative is beyond inputs of negative 2, or for more negative inputs. So we can say f of x is negative from negative infinity to negative 2. So for inputs of negative infinity to negative 2, we get negative outputs. Everything else is positive other than our x-intercepts. So we can say that we are positive from negative 2 to 1, and then from 1 to positive infinity, because every other part of our graph is considered to be positive outputs, positive y values, but on those x-intercepts, our outputs are 0, which is not technically positive. Okay, so moving along, now we want to look at solving polynomial problems algebraically. And we say over the complex numbers, meaning that we can have imaginary solutions, and we want to make sure we note those. So our first polynomial here, 5x cubed minus 15x squared plus 6x minus 18 equals 0. Generally, when we are solving these, we want to fully factor. And our first technique that we're going to practice is factoring by grouping. Okay, so factoring by grouping, we want to look at our polynomial. We want to look at the structure of it. We want to see, do we have commonalities between our first two terms and our second two terms in this polynomial? And I can see that, yeah, we do. Well, 5 times 3 is 15, 6 times 3 is 18, so there seems to be something in common there. It's a good reason to try to factor this by grouping. So if I look at the first two terms, I say, well, I could factor out 5x squared. This would leave me with x minus 3. And if I look at my second two terms, I can factor out a 6. And that leaves me with x minus 3. So that initial observation that there seemed to be some relationship between 5, 15, and 6 and 18, 5 times 3 gives us 15, 6 times 3 gives us 18, that actually resulted in us being able to factor by grouping because we're able to factor out something from the first two terms and the second two terms, or the last two terms, and this is going to allow us to say that this is equivalent to 5x squared plus 6 times x minus 3. Okay. And this is as far as we can go as our factoring is concerned. I do not believe we can go any further. So now we want to use the zero product property to solve this equation. So we can say x minus 3 equals 0, and it's easy to see that x must equal 3. So that is one solution. We can also say that 5x squared plus 6 equals 0. And we want to isolate x, so we subtract 6 from both sides. Okay, we get 5x squared equals negative 6. We divide by 5 on both sides. We'll come up here. We get that x squared equals negative 6 over 5. We should recognize we can't square a number and end up with a negative. So when we take the square root, we're probably going to get an imaginary number. And so we square root both sides. Okay. And when we take the square root, in this case, we take plus or minus. So we end up with x equals plus or minus the square root of negative 6 over 5. Okay. And since we are taking the square root of a negative number, we can factor out our imaginary part. We can take the negative, or the square root of negative 1, factor this out of negative 6/5, and we know that the square of negative 1, square root of negative 1, we can write as I. So this is plus or minus I square root of 6/5. So these are our three solutions. We end up with x equals 3, x equals I times the square root of 6/5, and x equals negative I times the square root of 6/5. So this actually accounts for two of our solutions because we have the positive and the negative just wrapped up together with that plus or minus. And this makes sense. The fundamental theorem of algebra tells us that with a degree of 3, we should expect to see 3 solutions to our equation when set equal to 0, or 3 x-intercepts. Okay, our second problem gives us another opportunity to factor by grouping. So let's change the color here. We see 2x cubed minus 3x squared plus 8x minus 12. So if we look at our first two terms, we have 2 and 3 as our leading coefficients, or 2 and negative 3. We have 8 and negative 12. And to get from 2 to 8, we multiply by 4. To get to 3 to 12, we multiply by 4. So this is kind of a sign that, we may be able to factor by grouping here. So here I'm going to look to factor out my x squared, the greatest common factor of my first two terms. And so I take out x squared, leaving me with 2x minus 3. My second two terms, my greatest common factor is 4. And I'm able to be left with x minus 3. 2x minus 3. And so I have this common factor of 2x minus 3 in my first two terms and my second two terms. So I'm left with x squared plus 4 times 2x minus 3. And x squared plus 4, we cannot factor any further. It is not a difference of two squares because of the plus. So this is as far as we can go. And now we're going to take our zero product property, and we can solve. So we can say 2x minus 3 equals 0. We add 3 to both sides. We say 2x equals 3, divide by 2, and we get x equals 3 halves. So one solution is x equals 3 halves. Because we are degree 3, fundamental theorem of algebra tells us to expect 2 more solutions. So we set x squared plus 4 equal to 0. We subtract 4 from both sides of the equation, and we get x squared equals negative 4. Okay, so we can expect to see imaginary solutions. We have x squared resulting in a negative number. When we take the square root of x squared, we want to remember that we end up with x equals plus or minus the square root of negative 4. When we have the square root of a negative number, we can factor out the square root of negative 1. Okay. And then we get x equals plus or minus I square root of 4. And we know that the square root of 4 is 2. So x equals plus or minus 2I. And so those are our other two solutions. Because if we were to write them all out, we can say x equals 3/2, can also equal 2I, and it can equal negative 2I. Okay? So this is a way that we could write all three of our solutions. Sometimes we just write plus or minus 2I to condense those two into a simpler format. Okay, so those two examples talk about factor by grouping. Our next examples will be a little different. So let's change color again. In part C, we have 2x to the 6th power minus 7x cubed equals negative 6. So when we're solving these polynomials and these equations, it's generally a good idea to set them equal to 0. The zero product property is going to be our friend. So we're going to add 6 to both sides, and we get a new polynomial function, 2x to the 6th minus 7x cubed plus 6 equals 0. Okay, now here we want to recognize that the degree of our first two terms, x to the 6th and x cubed, well, these are, one is double the other. 6 is double 3, which means this is generally of the quadratic form. And our final term is just a constant number. So that means we can turn this into a quadratic and treat it as a quadratic to use some of our quadratic factoring techniques. So what we do is we can say let x to the 3rd power equal u. And we're going to substitute in u for any x cubeds we have. And how we can do that is we can rewrite x to the 6th as x cubed to the 2nd power using our properties of exponents, minus 7x cubed plus 6 equals 0. And then every time we have an x cubed, we want to replace it with our u. So we can say that 2u squared minus 7u plus 6 is equal to 0. And now we have something that's just a more familiar quadratic. We have u squared minus u plus 6. So that's just basic standard quadratic form. We can look for factors of AC, which is 2 times 6, or 12, that add to b, negative 7. And in this case, that will be negative 4 and negative 3. And when our a term is not 1, we usually have to factor by grouping and splitting the middle term. So we use that negative 4 and negative 3 to split this middle term. So we have 2u to the 2nd power minus 4u minus 3u plus 6 equals 0. Okay, and now we factor by grouping. We can pull out 2u, and we are left with u minus 2. We can also pull out negative 3. We are left with u minus 2. Okay, and we're going to go over here. So we're able to factor out 2u from the first two terms. Right? Here's our two terms. We're able to factor out negative 3 from our second two terms. And we are left with 2u minus 3 times u minus 2 equals 0. Wonderful. We've fully factored and can use the zero product property. Only thing to remember is we actually substituted in u for x cubed. So now that we've done our factoring and used our quadratic techniques, we want to put back x cubed. So we can say 2x cubed minus 3, and we can say x cubed minus 2 equal 0. All right. So now we use our zero product property. We can say that 2x cubed minus 3 equals 0. We can also say that x cubed minus 2 equal 0. Okay. We'll end up with x cubed equals positive 3/2. We will also end up with x cubed equals positive 2. We take the cube root of each side and we get x equals the cube root of 3/2. And we end up with x equals the cube root of 2. And this is a little interesting. So these are our solutions that we come to. But it's odd because our fundamental theorem of algebra tells us that, well, we had x to the 6th. Shouldn't we have 6 zeros? And it doesn't really appear like we have multiplicities of 3 for each of these solutions. And the truth is we don't. There are a couple other imaginary solutions to this function. However, we don't really have the techniques to be able to find the other imaginary solutions. So for the purposes of this problem, finding these real zeros for part C here is okay. You won't see something like this on the test, or if you did, it would only ask for the real zeros, because we really just don't have the techniques to get the other imaginary zeros right now. So we're going to take a look and we're just going to say these are our 2 solutions. We know based on the fundamental theorem of algebra there are 4 other imaginary zeros, but we don't have the techniques to find those right now. Okay, in our last factoring problem here, we have x to the 4th plus x squared minus 2 is equal to 0. So, change our color again. Well, we see that we have x to the 4th and x squared and then a constant term. So that tells us that we can do this u substitution type idea. We can turn this into quadratic form. So we can say let x squared equals u. We can say x squared squared plus x squared minus 2 equals 0. And then we can substitute in u anytime we see x squared. So we can say u squared plus u minus 2 equals 0. We use our quadratic factoring techniques now. What multiplies to negative 2 and adds to 1? Well, that would be 2 and negative 1. So we can factor this into u plus 2. U minus 1 is equal to 0. But then we have to remember, okay, u is x squared. So now that I've factored this, I've used my quadratic techniques, I'm going to put in x squared back where I have my u's. Interesting here, we are not fully factored. We have a difference of squares. So x squared minus 1. X squared is a perfect square, and 1 is also a perfect square. So we have a difference of squares. We could fully factor this into x squared plus 2 and x plus 1, x minus 1. Okay. Now we can use our zero product property. So we can say x squared plus 2 equals 0. We can say x plus 1 equals 0, and x minus 1 equals 0. Well, our second 2 give us zeros of x equal negative 1 and x equal 1. Then our first equation, or our first factor, we can write as x squared equals negative 2. When we subtract 2 from both sides, we square root both sides and we get x equals the square root of negative 2. We can say, okay, this means that x is equal to the square root of negative 1 times the square root of 2, or x equals I square root 2. However, when we take the square root of x squared, we have to remember to take plus or minus. So we take the positive and the negative. So x actually equals plus or minus I root 2. So we can say x equals positive I square root 2. X also equals negative I square root 2. Okay. And this provides us with the 4 solutions that we would expect to find with a degree 4 polynomial based on the fundamental theorem of algebra. So for the even roots, we are able to actually find those imaginary solutions. It's for the odd roots that we actually don't have those techniques at the moment. All right, looking at number 14 here, we're going to just practice our polynomial division. So it says to divide x cubed plus 8x minus 3x squared minus 3, or minus 23 by x minus 3. And this practice problem is nice because we will end up with a remainder, so we can see what our options are for when we have a remainder. First thing to note is that this is not in standard form, so we want to put our polynomial into standard form as our dividend. Okay, then we're going to divide by x minus 3. Looking at our lead term, we know that we must have x squared times x gives us x cubed minus 3x squared. And we subtract, minus minus becomes plus, and we are left with 8x minus 23. Okay. X goes into 8x 8 times, so we put plus 8, multiply it back, and we end up with 8x minus 24, and we are subtracting, cancels, leaving us with a remainder of positive 1. Okay, so a couple options that we can say here is that our quotient is equivalent to x squared plus 8 with a remainder of 1. We can also write this as x squared plus 8 plus 1 over x minus 3. Okay, and we know that when that is multiplied by x minus 3, we end up back with our original polynomial. Okay, for problem 15, we are going to be writing the equation of a polynomial function f of x. So it says let f of x be a quintic, meaning degree 5, polynomial with zeros at x equal 3, x equal 2, and x equal negative 4. So right away I see that I only have 3 zeros when I would expect 5 based on the fundamental theorem of algebra. So I'm probably thinking that we will have a multiplicity for some of these. And we are told that the graph crosses the x-axis at 2, 0, and it bounces off the x-axis at 3, 0, and negative 4, 0. So to get to a degree 5 and meet all these criteria, we're going to have to say that x equal 2 has a multiplicity of 1, x equal negative 4 has a multiplicity of 2, and x equal 3 has a multiplicity of 2 as well. Because this gets us to a degree 5 and meets the criteria of crossing the x-axis at 2, 0 and bouncing off at 3, 0 and negative 4, 0. So our basic polynomial that we can write in factored form would just look like f of x equals x minus 3, x minus 3. That's our x equal 3 solution with a multiplicity of 2. Then x equals 2 gives us x minus 2 from here. And x equal negative 4 gives us x plus 4, x plus 4 for our multiplicity of 2. So this is our most basic version of the f of x that meets our criteria of having these zeros. Okay, but we need to note that our polynomial here is going to have an f of 1 equal to 100. So an input of 1 for x provides us with an output of 100. And to account for this, we're going to put an a value out in front. And we're going to say, we know that these factors all exist for our function. So we're going to leave our factors, and we're going to account for f of 1 equaling 100 by putting an a value and solving for what must a have to be to make this true. So I'm going to replace f of x with 100. Okay. And I'm going to say it's equal to a. And then I'm going to substitute in 1 for all of my x's. 1 minus 3, 1 minus 3, 1 minus 2, 1 plus 4, and 1 plus 4. So I end up with 100 equals a times negative 2 times negative 2 times negative 1 times 5 times 5. Okay, and so negative 2 times negative 2 gives us positive 4, times negative 1 gives us negative 4, times 25 gives us negative 100. So we get is that 100 equals a times negative 100, therefore a must equal negative 1. So our polynomial in factored form that goes through the point 1 comma 100, or where f of 1 equals 100, must be f of x equals negative x minus 3, I'm going to write squared, x plus 4 squared, x minus 2. Okay, so the key thing here is we know a point on this polynomial function, which just allows us to get an a value out in front and be a little bit more specific to our polynomial. The next problem is going to do the same polynomial function, but this time we have a different point that we know it goes through. So here we know it goes through the point 1 comma negative 50. F of 1 equals negative 50, or when we put in 1 for x, we get an output of negative 50. So we can set up the same equation, but this time we sub in negative 50 equals a. I'm going to write it as x minus 3 squared, x plus 4 squared, x minus 2. Okay, and replacing my x's with 1, I get negative 50 equals a, 1 minus 3 squared, 1 plus 4 squared, 1 minus 2. Negative 50 equals a. 1 minus 3 is negative 2 squared is 4. 1 plus 4 is 5. 5 squared is 25. 1 minus 2 is negative 1. We multiply these all together, and again, we actually get negative 100. Which makes sense. When we plugged in 1 before, we got negative 100. We would expect to get it again. So negative 50 equals a times negative 100. We divide both sides by negative 100, and we simplify and we get a equals positive 1/2. So this function would have to be f of x equals 1/2 x minus 3 squared, x plus 4 squared, x minus 2. So we account for our point that we go through, f of 1 equaling negative 50, with our a value out in front of our polynomial. And we have one more problem here. Write the polynomial f of x in factored form if the point 0, negative 864 lies on the graph of f of x. So this is just a different format of saying the same thing. We could say f of 0 equals negative 864. When we put in 0 for x, our y value or our output is negative 864. So we can use our same polynomial as before. We can say negative 864 equals a. I'm going to substitute in 0 right away. 0 minus 3 squared, 0 plus 4 squared, 0 minus 2. Negative 864 equals a. Negative 3 squared gives us 9. 4 squared gives us 16. And negative 2. Okay, so I'd want to multiply 9 times 16 times negative 2, and we get negative 288. So negative 864 equals a times negative 288. I can divide by negative 288 on both sides to get a. And if we divide, we get a is equal to 3. So to write f of x in factored form, I can write f of x equals 3, x minus 3 squared, x plus 4 squared, x minus 2. Okay, so we're in factored form, and we go through the point 0, negative 864 by having a value of 3. All right, hope you liked this video, and don't forget to subscribe to my YouTube channel.